Hello everyone, welcome back to Introduction to Semiconductor Devices. In the last week, we studied the basics of operation of a MOSFET. We looked at the saturation, the linear and the subthreshold regimes of operation. And then we have also derived some basic expressions for current as a function of gate and drain voltages. So what we have studied so far can be termed as classical MOSFETs. Okay? Simple square law theory works there. And these were the MOSFETs that were predominantly used in the 60s and 70s. Okay? So after that, there have been a lot of developments. And today we will try to give you a perspective of what happened in the last 40 years or so. To start with, I would like to introduce the concept of scaling. Scaling was first proposed by Dennard and co-workers in the year 1974. So the essential idea is this. So we have the MOSFET, we have seen this. We have the source, the drain, and the oxide thickness, and the gate, and all that. So we have the various parameters of this MOSFET, such as the length here, and then there is this width which is going into the plane of the sheet here, and then there is oxide thickness, and then the doping concentrations. Right? These are the most important parameters to calculate the threshold voltage and so on. So what Dennard proposed in 1974 was this. Let's reduce the vertical and the lateral dimensions by a factor alpha. So what we can do is, let's say we have the length L, I'll make it alpha times L. So I'm introducing a scaling factor, which I'll call as alpha. Okay. And most of the time, this is, for today, we will assume that it is 0.7. Alpha equal to 0.7. So we are essentially reducing the size by about 30%. Okay. So we make alpha as 0.7. And if L was initially 1 micron, then after the scaling, L becomes 0.7 microns. Okay. Similarly, I would also reduce width by the same scaling factor. And also the thickness and so on. So all the lateral and the vertical dimensions, for example, Tox is a vertical dimension. So I'll make Tox as 0.7 times Tox. Right. So I'll do this sort of a scaling. Along with that, I will also scale my supply voltages. For example, the power supply VDD and the threshold voltage. So VDD, I'll scale it as alpha times VDD. And let's say VT, I'll scale it as alpha times VT. So I'll reduce my supply voltages and the threshold voltage. And lastly, we would also increase the substrate concentrations, or all the doping concentrations. For example, if I have a drain concentration of, let's say, N plus, then in the scale geometry, I'll make it N double plus. Okay, for example, here N plus in the original MOSFET. Once I shrink the sizes, I get a scale MOSFET like this. All the sizes are smaller, but the doping concentrations are higher in this case. There's a reason why this was proposed. We don't want to get into all that, but right now I just want to tell you, what is proposed and how it is beneficial to us. Okay. So the doping concentrations are also scaled for some practical reasons. All right. So we are left with, from the original MOSFET, a much smaller dimensional MOSFET with higher concentrations. So what? Why should this matter to us? Well, it matters to us because we'll see that this scaling will actually improve performance. Okay. To show you that, I will go step by step and compute some parameters here. So to start with, I'm assuming that the lateral dimensions and the vertical dimensions are reduced by 30%. That means, let's say initially W was 1, I'll make it 0.7. L was 1, I'll make it 0.7. Tox was 1, I'll make it 0.7. Okay. It's just shrunk by 30%. Similarly, the voltages are scaled by the same 30%. So we did VDD of 0.7 and VT of 0.7. Okay. So now we want to see what happens to these parameters after scaling. To start with, die area. Maybe I shouldn't call it die area. Let me call it MOSFET area. Okay, dies. Basically, on a chip, you fabricate various devices. So you make blocks. We call them as dies. But anyway, for our purposes, it doesn't really make any difference. We can just call it MOSFET area. And we are only looking at the active region, where under the gate. Okay. So this area for a MOSFET would be W into L, right? You have a length and width, that is the area under which you have inversion layer forming. So this, what happens to W into L? Once we scale it, it becomes 0.7 into 0.7, that should be equal to 0.49. So after scaling, the MOSFET area reduces by 50%. Right? Well, nothing very surprising so far, right? That's what we would expect, reducing the sizes. What happens to the total gate capacitance? Well, remember this total gate capacitance is in farads, okay? So the expression for this is, let me call it CG, will be Cox, which is the capacitance per unit area we have defined for oxide, times the width into length, the area, right? So this will be equal to epsilon oxide by T oxide into W into L. So if I scale it, epsilon is a material parameter, it does not change. So I'll still retain that, but thickness has scaled. So I'll say divided by 0.7 into 0.7 into 0.7, right? So what I end up getting is 0.7 times reduction in the gate capacitance, okay? So this reduces by 30%, right? Okay. What about gate capacitance per unit area? Okay. Gate capacitance per unit area we have already seen. This is simply Cox, and that will be epsilon oxide by T oxide. So this reduces by, or rather, it's divided by 0.7. So effectively, it turns out to be equal to 1.43 into whatever the original capacitance. Okay. So it increases by 43%, or let's just round it off to 40%. Okay. So this increases by 40%. Why are we doing this? Well, we are just trying to evaluate these parameters so that we can draw some conclusions of what happens in a scaled MOSFET, or if you shrink the size of a MOSFET, what happens? Okay. So now what happens to current? Okay. We know the expression for current. ID is basically mu Cox W by L. I'll take saturation current. So I'll simply say VGS minus, there is no harm in doing this, by 2L, right? So this is my ID expression. And remember in this ID expression, this is per unit area. Cox is capacitance per unit area. Okay. So let's substitute and see. So mu anyway is a material parameter, I don't care. Cox is 1 by 0.7. W and L both will scale by 0.7, so they'll cancel out. So I'll be left with 0.7 square. So what you see is the current in a MOSFET reduces by 30%. And what happens to the delay? So delay is an important parameter in any MOSFET circuit. The reason is, if you think about any digital chip, right, we are dealing with logic 0 and logic 1. So essentially the transistor is switching between 0 and 1. And the simplest way to model this is in form of an RC circuit. So what happens is, let's say if I have a MOSFET, I'll take a small, let me take a MOSFET, and then I will, basically MOSFETs are going to drive some loads. Okay, typically the output of a MOSFET will be given to the input of another MOSFET, which is essentially, input means gate. So gate will present a capacitance. So I can model in its simplest form a MOSFET circuit as, simply a RC network. Okay, so the capacitor, the load is capacitance C, and MOSFET I can model as resistance. Okay, so when I have RC network, I know what I have studied in basic circuit theory what happens, right? We analyzed it. You would have analyzed it in great detail. So what is the time it takes to charge a capacitor in RC network? Well, essentially, it's going to depend on the constant, time constant, RC, right? And in this case, let's say I want to charge it to a certain voltage V, and I know that the MOSFET is contributing a current I. So the time to charge the capacitor will simply be, I'll call it T delay. Okay, that is going to be, the capacitance is C, and you want to charge it to voltage V, right? So C into V will give you the charge, And if I divide it by the current that is flowing through the MOSFET, right, then I'll get my time that it takes to charge the supply that much of charge on the capacitor. So time delay. Okay, and clearly, this capacitance is going to be the total capacitance of the oxide. So this will be 0.7 into voltage will be scaled by 0.7 divided by current will be scaled by 0.7. So roughly this will be equal to 0.7. Okay, so the time delay has reduced by 0.7. Why is this important? Well, the reason it is important is in a digital circuit, let me try to demarcate this out. In a digital circuit, you will have switching behavior, like you'll have an input which switches and so on, right? You'll have cycles like this. So the time delay, this is going to be a T, and the frequency of operation is going to be determined by the time delay. Simply frequency is going to be inversely proportional, is going to 1 over T, right? So if your time delay is small, I can switch my circuit faster. That means I can charge and discharge. So essentially I can perform a lot of operations. Okay. So if my time delay is reduced, my frequency of operation is increasing. If it's reduced by 0.7, that means it's reduced by 30% here. Well, in my notation, I should call it 30%. Right? Then the frequency will increase by about 43%. Okay. And finally, the power dissipation is another important metric. So we said that RC network is essentially a simple model of a MOS digital circuit. And if you're trying to charge a capacitor to voltage V, then the amount of energy stored in the capacitor after charging is going to be half CV square. Okay. So you turn on the MOSFET, you charge it to half CV square. You turn it off, that voltage will the energy will be dissipated in the resistor, okay, or in the MOSFET, across the MOSFET, and the total amount of energy will be in the process you lose CV square of energy. So the dynamic power dissipation of a MOSFET, the dynamic, is going to be CV square into frequency. Well, I mean, if you study any digital circuits course, you will actually go into greater detail of what is dynamic power dissipation, static power dissipation, and so on. But for now, I just want you to accept that if you have a C as a capacitance and the V as a supply voltage, the total amount of power dissipated when you are switching up 0 to 1 and 1 to 0 is going to be CV square F, where F is a frequency. So what happens to this parameter? Well, C is reduced by 0.7, voltage is 0.7 square, and F is basically 1 over T. So this will be divided by 0.7. So what you end up getting is, this is going to be scaled by 0.49. Okay. So power dissipation reduces by 50%. Okay. So what happened because of scaling? When you shrink your sizes of MOSFETs, you are first of all making it the MOSFET smaller, right? You are making it faster, and you're also making it power efficient. Right? So these are very, very good properties to have. Okay. So digital circuit has become much more efficient. And this is the basic reason why scaling process is adopted. Okay. So this was as simple as that. Okay. So if you look at the impact of scaling in the 1970s and 80s and even early 90s, that is captured in this graph. So what you're seeing is basically the frequency of a microprocessor over the years from 70s to 2000. Okay. And many of you may not even know or remember or be aware that in the 80s or even 70s, the frequency of the processors was basically few megahertz. 80s, it was hundreds of megahertz. So the 286 processor was having maybe 200 megahertz or 100 megahertz or so. Let's say. So here 286 processor, which is one of the popular. This is 10 megahertz. Okay, that's even smaller. By the time we come to 386, it is still 25-50 megahertz. And finally, when you come to Pentium, it's hundreds of the first original Pentiums were about 100 megahertz or so. And then finally, they kept on increasing. The reason this happened was the process of scaling that I described. So this increase is because of scaling. Of course, a lot of technology was developed to achieve this. But over time, in the last 30 years, we have tremendously improved the processing capability of the MOSFET. So if you take, let's say, when you are actually designing a processor, one of the most important features is power dissipation. Let's say power dissipation, we can accept about let's say 100 milliwatts, or not 100 milliwatts, 100 watts of power dissipation. Okay, in your chip. So if you scale a particular technology and make it smaller, what happens? We are able to have more transistors, double the transistors, double number of transistors for same power dissipation. Okay, because we saw that the power dissipation reduces by 50%. So effectively, you can increase the number of MOSFETs by the same amount. You can make the number of MOSFETs double and still have the same power dissipation. And then what else? The time delay has reduced, so the frequency of operation also has increased, right? By about 42% or 43% we saw. So overall, this scaling process has enabled the technology to evolve over the last 30 to 40 years. Okay, it might seem very simple. Well, the idea is quite simple, but implement it took a lot of. It was a lot of. We had to overcome a lot of challenges. You might have heard of nanotechnology nowadays. It's a very popular term. But the entire field of nanotechnology, I could say, was developed so that the tools and techniques of nanotechnology were developed so that we can achieve scaling in the MOSFETs. So in that way, the MOSFETs are the driving force of nanotechnology. Even today, the forefront of nanotechnology is actually what we use in the IC industry. All right. So this is the background, and so this leads me to the next step, which we call as Moore's law. You might have heard about Moore's law. In the 1960s, Gordon Moore, who was the chairman of Intel, he predicted that the number of transistors in a chip effectively doubles every 2 to 3 years. Okay, so we want to understand what that is, and while we are trying to understand that, I would like to introduce a term which we call as a technology node. Okay. So this is very important because even today you might, if you follow the technology news, you will see that Samsung has come out with 5 nanometer technology, or Intel has demonstrated 5 nanometer technology and 3 nanometer technologies in the research stage. So what does it mean? Okay, that's what we would like to introduce. So in the previous lectures, we have shown you how the MOSFET looks like. We have shown you the top view, the side view of the MOSFET. So if you look at it from the top, a MOSFET will have the source drain regions separated by a gate region, right? So this is the top view we said, source, drain, and the gate. And on a chip, you can have many such MOSFETs. So for example, I can have another MOSFET, which will be adjacent to that. So let's say it has the same width and some gate length. Okay, this is another MOSFET. Now, one of the prominent or important features of a technology is the spacing between these two MOSFETs. Okay, so of course, in between them, you have this what we'll call as the isolation region, field oxide, or nowadays it is called shallow trench isolation, different technologies. Essentially, you don't want these MOSFETs to communicate with each other, right? So we'll have what is called as field oxide in the older times. Now it is STI. Okay, so now the important parameter to characterize a particular technology is this distance, which we'll call as gate pitch. Essentially, how close can your transistors be in a particular technology? Okay, so of course we would like them to be 50 nanometers apart or 10 nanometers apart, but that's not going to be possible, especially if you don't have the tools to achieve that sort of a precision. Okay, so and this is what was called as the technology node parameter. Of course, I'm being very I'm only giving a qualitative description. There's a more precise description of this, which we'll call as the distance between the half pitch of DRAM cell. So DRAM memory is basically always the most aggressive form of scaling. So you have the memory chips which are scaled first. So they are the smallest devices we make. And if you look at the distance between two gates and look at that is the pitch and take the half of that is called as the technology node parameter. Okay, so if you look at 1970s, this was about 3 microns, and by 80s it became 1 micron, and by mid 90s, let's say this parameter became 250 nanometers. So what this number is telling you is essentially, it's simply a parameter to capture minimum feature sizes, minimum or, or capture the smallest distance between MOSFETs. Okay, the smallest distance between MOSFETs. This was in the past, but nowadays, we actually, the meaning is lost actually nowadays. It doesn't physically represent anything. It is just that, this notation has been continued, it's being used even today. Okay. So what happens is, let's take one number. Okay. Let's start with, let's say 250 nanometers, right? So I can say 250 nanometers, I'll write it here. I'll take that distance, that particular technology. This was, I think, demonstrated in 95, let's say, approximately. What I'll do is, I'll shrink it by a factor 0.7, 0.7x. What happens? What do you get? The feature size now will be close to 180 nanometers. Okay. And then if you shrink it again by 0.7 times, this will be 130 nanometers. And if you shrink it again, you get 90 nanometers. Okay, sorry, shrink it by 0.7. Okay, and so on. So if you want to write out more, it will be 40. After this, it was 65 nanometers, and then that led to 45 nanometers, and that led to 45 nanometers would lead to 32 nanometers. That would lead to 22, I believe. 32 into 0.7 will be 22 nanometers, and then 14 nanometers. Then it will come to 10 nanometers, and then 7 nanometers, and then 5 nanometers. Okay. So essentially, what we are doing is we are physically packing more transistors, and we saw that when we scale it by 0.7x, the area reduces by 50%. So essentially, we can increase the number of transistors. I mean, we can double the number of transistors. Okay. If you take a certain chip in, let's say, 250 nanometer technology. Okay. When I say 250 nanometers, or sometimes we also call it as 0.25 microns, micrometer technology, micron technology. So what this means is, the smallest MOSFETs that you can make are roughly of the order of 0.25 microns. Okay. This is a very nowadays the term doesn't have any precise meaning. It's essentially simply to capture the number of transistors is doubling. That's it. Okay. Sometimes it also nowadays it means that the effective performance of the processor is, or your chip is effectively like as though it is scaled by this distance. Okay. So this is called as nodes, technology nodes. Okay. These numbers are known as technology nodes, and we see that over the last 40 years, there is a continuous decrease in the number of technology, the size of the technology nodes. And this is a log scale, you see, mind you, this is on the log. So you're seeing almost an exponential reduction in the sizes. Okay. And this 250, let's say if you take 250 nanometers, this was somewhere in 95. The ones I remember or what I have encountered personally were basically, I think 90, which was introduced maybe I think 2003, 65, which is 2005, and then 45, which was in 2007, and then 32 in 2009, 22, I think in 2012. It took a little bit of time because Intel introduced FinFETs there, and then 2014, 2016, 2018, and 2020. So what you're seeing is every 2 years, the number of transistors on a chip is essentially doubling. Okay. So this is what was, what the famous prediction of Gordon Moore was, and we sort of, the semiconductor industry tries to keep up with that sort of a trend. Okay, even though effectively now the transistor size is definitely not, you don't have two transistors spaced by about 5 nanometers. It's not true. It's much more complicated than that. But we still use this notation, in a kind of a homage to Gordon Moore's, prediction. Okay, so essentially, the number of transistors doubles approximately every 2 years. Okay. Or effective performance, I could say, of the transistors doubles every 2 years. All right. So this is what is known as technology scaling and Moore's law. Okay. This is Moore's law. Okay. So while we do this process, the performance improves significantly. Okay. It turns out that this is not that simple. There are various challenges. Of course, if you try to ever fabricate a PCB, you would have seen that, the PCBs that you see in your computers or in any electronic components, they have these fine copper lines which are connecting into electronic components. And if you try to fabricate them at home, you will see that it's quite challenging to make very fine features. Now we are talking of nanometer scale features. How do we do that? It's a whole lot of a difficult process, but thankfully, semiconductor technology or IC industry has developed these processes so that this can be realized. Okay, so I will in the next couple of in the next video, I'll stop this video now. In the next video, I'll talk a little bit about what are the various challenges in scaling and what are the limits, some of the limits, and then we'll take it forward from there. All right. Thank you very much for your attention.